Good morning, all of you. So in the previous class, this and gameplay. So in that, I told you that when we have a big problem, we need to divide the big problem into smaller number of subproblems, so that we can solve the smaller number of subproblems, and we are going to solve them separately. And after solving those things, we need to add all those solutions, and we need to get the final solution. So this is an effective way. So an effective way of solving a complex problem is to reduce it to simpler parts and solve each part separately. After getting the answer, we're going to merge all those. Okay. So this particular reduction enables us to obtain an elegant solution to the problem. So this particular reducing the problem, solving them, and solving the subproblems is nothing but so this particular structure is known as the AND/OR graph or AND/OR tree. So this particular AND/OR graph is useful for representing the solution of complicated problems. So whenever we have to solve the complicated problems, we need to use AND/OR graphs for representing the solution of complicated problems. Okay. So the decomposition of a particular problem, it generates the arcs, which we call as AND arcs. That means those arcs will the generated arcs for a particular problem will be known as the AND arcs, AND arcs. Okay, one AND arc may point to any number of successors, and all those should be solved. Okay? Next. So coming to the problem reduction or AND/OR graph or Weierstrass algorithm. So these are the names for problem reduction. So problem reduction using AND/OR graph or Weierstrass algorithm. Right. So let us see an example here. Right. So suppose we are given a problem, and that problem is divided into simpler subproblems. And after solving each and every subproblem, we need to combine all the solutions of subproblems, and we need to obtain the final solution. Right. So a particular problem can be solved in many number of ways. So whenever we are given a problem, it can be solved in many number of ways. Okay. So this particular AND/OR graph is nothing but one representation of dividing the complex problem into subproblems. Okay. So this particular AND/OR graph provides simpler representation of complex problem that leads to better understanding. That means by dividing the complex problem into subproblems using AND/OR graph, we can understand the problem in a better way, right? So, for example, consider an instance called as if we wish to own a cellular phone. Suppose I want to purchase a cell phone, right? Then it may be possible that either someone gives it to you, or else you can earn money and buy one for yourself. That means there are two ways to have cell phone. One is whether anybody or somebody can gift that cell phone to me, or else I can earn money and buy a cell phone for me. Okay, these are the two ways, right? Office, I get it office. Okay, so one way here is suppose I want to purchase a cell phone. Suppose I want to have a cell phone, or I want to have a cell phone. I need a cell phone. Okay, how do we get a cell phone? Whether either somebody can gift that cell phone to me, or else I can have some money, and using that money I'm going to purchase a new mobile phone. Two ways. One is gift, as a gift. One is as a gift, or else purchasing. Gift or purchase. That's it. Okay, two ways. Okay, now let us see how to represent this particular instance in AND OR graph. Okay, see this one here. Own cellular phone. So this is the instance. Own cellular phone. That means to have a cell phone, right? So these are the ways. One is get a gift. Either somebody can gift it to me or else earn money and buy it. So here, see this one here. So this particular arc represents me as and earn money and buy it. So two ways. One is get a gift or earn money and buy it. So this is nothing and I'm applying and between earn money, buy it. So here this one. So this one and here and means like this. This like this I have to draw an arc, right? Next, so either get a gift or else earn money and buy it. So this is nothing but the AND OR graph representation. Okay. Now let us see. Now let us consider another problem known as towers of Hanoi. Okay. So this particular towers of Hanoi is a mathematical game or puzzle. So this is a mathematical game or puzzle. So in this towers of Hanoi, it contains three rods, and a number of discs of different sizes, which can slide onto any rod. That means like this. So see the first figure. See the first figure. Okay, here I have three discs here. Here I have three discs. Okay, three discs and three rods there. A, B, C are the rods here, and green color, violet color, and red color. These three are the rods. These three are the discs. DISKS. The discs. Three discs and three rods are given to us. Okay. Now let us see. Okay. Now see the example. Let us consider. So this particular towers of Hanoi contains three rods and a number of discs of different sizes, which can slide onto any rod will be given to us. Okay. So, so I was given three rods and I am given three discs here. Okay. So the which can slide onto any rod. That means any disc can move to any rod. Okay. Next one is the puzzle starts with the discs being stacked in descending order of their sizes. Descending order means see this one. So the initial state is here. Okay. Initial state. Okay. So initial state is here. So this one. This is given and I need to place the rods like this in seventh finger. I have like this. I need to place the rods. So I have I was given the disc. I was given the disc like this. I was given the disc like this, and I need to place. And my goal state is so all the discs that are in A must come to third rod like this. That means on the top the smaller disc, and after that the large disc like this. Like that I have to place the rods like this. Okay. So this is the goal state. So this is the goal state, and this is the start state. Okay. All the discs that are in A must come to C like this. Okay. So this is the example. Right. Now see. So the puzzle starts with the disc being stacked in descending order of their sizes, with the largest at the bottom of the stack and the smallest at the top, thus making a conical shape. Okay. So that means the smallest disc should be on the top and the largest disc should be at the bottom. So that is our goal state. Now, the objective of the puzzle is to move the entire stack. The objective of the puzzle is to move the entire stack to another rod by using the following rules. Now, some rules are also being given to us. Okay. So only one disk can be moved at a time. That means at a time I can move only one disk. Next, second rule is each move contains each move consists of taking the uppermost disk from any one of the rods and sliding it onto another rod on top of other disks that may already be present on that rod. Okay, that means the uppermost disk should be taken out from one of the rods and that should be placed onto another rod. That means the top of the topmost disk will be taken out and that will be placed onto a onto a onto a onto another rod. Next, on top of the other disks that may already be present. That is, if some rod, if some disk is already there, and that particular and this particular taken out disk should be placed on the other disk. Okay. Next, so third rule here is no larger disk may be placed on top of a smaller disk. That means smaller. That means the larger disk should not be placed on the smaller disk. That means on the top only the smaller disk should be there, and on the bottom the larger disk should be there. The reverse should not happen. That means smaller disk on the bottom and larger disk on the top should not be there. So these are the three rules. One is only one disk at a time can be moved. Second one is one of the disk will be taken out and that will be placed on another rod or else on the top of any other disk. And third one is no larger disk may be placed on the top of a smaller disk. So these are the three rules that have to be followed, right? Now see this one, problem detection. Okay. Right. Okay. Now see this one. So uh, see this one. These are the three rules that are given to us. Now, So this particular towers of Hanoi puzzle can be solved by using this particular. That means the number of moves I can make are decided by you have has the formula 2 power n minus 1. 2 power n minus 1. So here n is the number of disks. N is the number of disks. Okay. Here I have 3 disks. That means n value is 3. So 2 power 3. 2 power 3 means 8. 8 minus 1 means 7. That means total in total I have 7 moves. So in 7 moves I need to solve the problem. Okay. So these are the 7 moves that I'm using here to solve the towers of Hanoi problem. Okay. Say this one. Okay. So initial image. So on I have 3 rods A, B, C. On the rod A, I have 3 discs. Red one, next violet one, and the next one green one. So red, violet, and green. Now the first move I'm here is see the first image. So on C, that is C has the smaller. C has smaller. Now I am picking up the green disk and I am placing that green disk on rod C. Okay. Next, now I am picking up violet disk and I play it in rod. Coming to third image. So picking the disk that is there in C and I am placing it on the top violet one, that is on rod B. Next, fourth image. So now I am picking up the disk that is there on rod A, and I am moving it to rod C. Okay, next one. Now I'm picking up the green disk and I am moving it to rod A. Next, now I'm moving the rod that is there on rod B and I'm placing that particular disk on the rod C. That means already one rod is there, already one disk is there on rod B, on rod C. I'm just keeping it on the uh, red color disk. Next, now I am moving green disk that is there on rod A and I'm placing it on the top of blue disk. Now that is my goal state I had. So this is the goal state I need to get. So that's why I got it. So like this, I can make 7 moves and I can move all the disks to the last rod, that is rod C. So this is how to solve the towers of Hanoi problem. Now let us see another example. So consider an AND OR graph where each arc with a single successor has a cost of 1. So each and every successor of a particular node has a cost 1. Now let us assume that the numbers listed in parentheses denote the estimated cost. So the number that is written in the estimated cost, and the next the numbers that are written in square brackets represent the revised cost of the path. Okay, and the thick lines indicate paths from a given node. So these are the 3 things. Okay, now see this one. See the diagram once. So initial estimated value, next one revised values, next one estimated values, revised values, next estimated values. Like that I need to get all the values here. Okay. Now let us begin our search from start node A. Start node A. and compute the heuristic values for each of the successors, say B and CD. B and CD. So these are the two ways. So I can go to B or I can go to C and D. Okay. Next. So now B has the cost 20. The estimated cost is 20. Next, so estimated cost. No. Say B and C comma D. Okay. Now, okay. Now the estimated initial estimated values are 20 and 19, right? Okay. So if I make a move from A to C and D, then I can make the move. That is now the estimated values to me are 19 and 8 comma 9. 19 and 8 comma 9. So those are the estimated values. Okay. 19 comma 8 comma 9. Next, the estimated cost of path from A to B. The estimated cost from A to B is estimated cost from A to B is 20. 20. Why 20? Because I need to add 1 as each and every node has already assigned 1. So 19 plus 1. Yeah, so total 20. Next, and that from A to C and D. A to C and D is 19. Why 19 means A to C 8 and A to D 9. So C plus that is 8 plus 9 17. So 17 plus cost of 2 arcs. That means the upper one is the next one. So 2 arcs A to C and A to D. A to C and A to D. 2 arcs. Okay. Now the path from A to C and D. A to C and D seems to be better than that from A to B. So now I need to see which one is better. So based on the better one, I need to select it. So expand the AND path by extending C to GH and D to IJ. D to IJ, C to GH. Now the heuristics of GHIJ are GHIJ. GHIJ. So GHIJ are 3, 4, 8, 7. So now I will get I'm going to get my and by performing and between G and H, I and J, I'm going to get 3 plus 4 plus 2 arcs 9. Next 8 plus 7, 15 plus 2, 17. So these values are then powered up and the revised cost of path from A to C and D that is 28. 28. So why 28 means 9 plus 17. So 9. So here 9. 9 plus 17 plus cost of R from A to C. Cost of R from A to C. Is the and alpha. So initialize the graph start node. But start node is not labeled as solved or unsolved through all paths. Now traverse the graph along the path. and to traverse along the best path and expect all the unexpected nodes on it. If the node is terminal, that means whatever node I am considering, if that is the terminal, no, and heuristic value of the node is 0, label it as solved, else label it as unsolved, and propagate the status up to the start node. If the node is a non-terminal, add its successors with the heuristic values in the graph. So I need to check whether that is the terminal state or non-terminal state. So terminal state means that is the that is the goal state. Terminal state is the that is terminal means if that particular if a particular node is considered as goal node, then that particular node is known as the terminal node. Okay. So if the node is non-terminal, non-terminal means it means non-goal state. Right. Add its successors with the heuristic values of the graph. So those the successors of that particular non-terminal node, the heuristic values in the graph are to be added. Now revise the cost of the expanded node and propagate the change along the path with the start node. Now choose the current best path. Next, if start node equal to solve, the leaf nodes of the best path from root are the solution nodes, else no solution exists. Now I need to check whether the start node is solved or not. The start node is solved, then the leaf nodes are the best path from the root of the solution nodes. Otherwise, solution doesn't exist. Now stop the algorithm. Next topic, game playing. So this is one of the major topic in AI, okay, in which we have well-defined states and rules, and this particular game playing requires intelligence also. So a game is defined as a sequence of choices where each choice is made from a number of discrete alternatives. So out of the alternatives, out of the many number of alternatives I have, I need to make a choice. Oh, which one is better, like that. Okay. So each sequence ends in a certain outcome, and every outcome has a definite value for opening player. Okay. Next. Next one. Games can be classified into two types. So there are two types of games. One is perfect information games, and imperfect information games. Okay. Perfect information games are nothing but in which both the players have access to the same information about the game in progress. That is whenever the game is going on. So both of the players who are playing the game have access to the same information. That means both the players will get the same information. Next, imperfect information games are those in which players do not have access to the complete information about the game. Okay. Perfect means both of the players will have the information, and imperfect information means the players do not have the access to the complete information about the game. Okay. Coming to the perfect information games, examples are tic-tac-toe problem and chess problem. Imperfect information is nothing but cards game, dice game, all this. The next topic, game problem versus state space problem. Game problem versus state space problem. So in this particular state space problem, we have a start state. In the state space problem, we have the start state, we have intermediate state, we have rules or operators, and a goal state. Okay. Now, in game problems also we have a start state. In game problems also we have a start state, legal moves, and winning positions. Okay. Now see this one. So in state space problems, we have states, rules, and goals. And in game problems, we have legal board positions, legal moves, and winning positions. So they are the comparison between state space problem and game problem. Now, state status labeling procedure in game tree. Status means status is nothing but win, loss, draw, like that. Okay, so these are the three types of labels. Three types of labels. Okay. Next, so status labeling procedure for a node with win, loss, or draw in case of a game tree is as follows. So if J is a non-terminal max node, then status of J equal to either win, loss, or draw. So when do the J will win? If any of the J's successor is a win. If any one of the J's successor is a win, then J will win. Okay. Otherwise, if any of the J, if all the successors, if that means win means if any of the J successor is win, then J will win. Or else, if all the J successors are lost, then it will be loss. Next, draw means if any of the J successor is a draw and none is win. That means nobody is winning, but any of the J successor is a draw, then the game will draw. Okay. Next, now if J is a non-terminal min node, okay, then so when do the J will win? So if all the J successor are win, then it will win. Next, if any of the J successor is a loss, then it will loss. And next, if any of the J successor is a draw and none is loss, then it will draw like this. Okay. Next, a game tree in which max plays first. A game tree in which max plays first. Okay. So this is the complete game tree with max playing first. Okay. Okay. So these are the winning moves or losing moves, like draw move, right? Okay. So if it is max, then if any of the that is, so max means this one. If any of the J successor is the win, then it will win. Like that. Like next. Next one is okay. So this is the game tree. So when do the max win, or when do the max loss, or when do the max so these are nothing but the representations, right? So if J is a non-terminal max, no, then how we represent the status like this. And if it is minimum, so for loss, for win, and for draw. And the first one is for win, right? Next one, max. So max tends to win. That means, so how do the, if it is a max node, then how do it win, or how do it lose, or how do it draw? So these are the representations of game tree. Okay. Next one, a game tree in which min plays first. If the min plays first, then the moves will be like this: the winning moves, or losing moves, or draw moves. Okay. Now see this one, min-max procedure. So this particular min-max procedure is a recursive or backtracking algorithm which is used in decision making and game theory. Suppose if anything happens, or if I'm not getting to ghosted, then I can backtrack. So this particular minimax procedure is a recursive or backtracking algorithm, and it is used in decision making and game theory. So this is mostly used for game playing in artificial intelligence, such as chess game, checkers game, tic-tac-toe game, and various and various other games. Okay. So in this particular procedure, two players will play the game. Two players. One is max, another one is min. Max will select the maximizer value, and min will be min will. So there are two players. One is max, another one is min. So max will select the maximizer value, and min will select the minimizer value. So max means maximizer value will be selected. Min means minimizer value will be selected. Next, the Minimax algorithm performs a DFS, that is depth first search algorithm for the exploration of the complete game tree. So this particular algorithm proceeds all the way down to the terminal node of the tree. Right. Next one. So this particular Minimax algorithm performs a DFS for exploring the complete game tree. So this particular algorithm proceeds all the way down to the terminal node of the tree, then backtrack the tree as a recursion. Okay, like this, the minimum, like the Minimax procedure continues. Now let us see the working of Minimax algorithm. So this particular algorithm can be easily described using an example. Okay. Below I have given a game tree that represents the two-player game. Okay. Now let us see the working of Minimax algorithm. So this can be easily described using an example. Now let us see the example of game tree. So here I have taken an example of two-player game. One is maximizer, and another one is minimizer. So maximizer always try to get the maximum possible score, and minimizer will try to get the minimum possible score. So okay. So maximizer and minimizer. Maximizer will get the maximum possible score. Minimizer will get the minimum possible score. Next, so apply DFS. So by applying DFS, that is depth first search, we need to go to all the way through the leaves to reach the terminal nodes. So so by following all the leaves, starting from the start node, we're going to reach the terminal nodes. Okay. At the terminal node, the terminal values are given. So we'll compare those values and backtrack the tree until the initial state occurs. Okay. Next. Now see this example. So these are the steps involved in solving the two-player game tree. Maximizer and minimizer. So the first step. So these are the terminal values. That is H, I, J, K, L, M, N, O. These are the terminal values. In the first step, the algorithm generates the entire game tree. Okay. So in the first step, the algorithm generates the entire game tree. Let us take A is the initial state. So let us consider A is the initial state here. Next, maximizer takes the first turn, and minimizer will take the next turn. Maximizer and minimizer. Maximizer takes the first turn, and minimizer takes the next turn. Here the maximizer is A in level 0. Level 1 is minimizer is B and C. Next one. Here the D, E, F, G are maximizers. Next H, I, J, K, L, M, and O. These are the minimizers. Okay. A is maximizer. B and C are minimizers. D, E, F, G are maximizers. And H, I, J, K, L, M, and O. These are the terminal nodes. Okay. Now, first we'll find the utilities value for the maximizer. We'll find the maximum among the all. For node D, max of minus 1 comma. For node E, max of 2 comma 6. Next, next for node F, so for node F, max of minus 3 comma minus 5. Next for node G, okay. For node F, so minus 5. Next for node G, 0 comma 7. Now I have to select max of 1 comma 4 is max. Max of 2 comma 6. The next max 0 comma 7, 7 is there. So later I will get the answers. Now in step number 3, now minimizer is to be considered. So for node B, in 4 comma 6. Node B, minimum 4 comma 6. That's 4. Next for node C, so in step number 3, now it is the turn for minimizer. So for node B, minimum of 4 comma 6 means 4. 4 is the answer. Next for node C, minimum of minimizer of minus 3 comma 7. So minus 3 is the answer. Like that, I'm going to get the answer. Right? Now, step number 4. Now, consider maximizer here. So now, maximizer will select the maximum value. Okay. So out of the maximum of all the nodes, it find out the maximum value and find the maximum value for the root node. So in this game tree, there are only 4 layers. Okay. So in the game tree, there are only 4 layers. One is hence we reach immediately to the root node, but in real games, there will be more than 4 layers. Okay. So see this one, A to B, B to D, D to I. Okay. So for node A, max of 4 comma minus 3 means max of 4 comma minus 3. Okay. Okay, so this is how to solve the problem. Next, another example. So now let us see what is time complexity and space complexity. So time complexity means as it performs DFS with the game tree, the time complexity is big O of VM. B is the branching factor and M is the maximum depth of the tree. And next coming to time complexity. So the coming to space complexity, the space complexity for min-max algorithm is also similar to DFS, which is big O of VM. Now, limitations of min-max algorithm. Limitations. So gets really slow for complex games such as chess, Go, etc. And coming to games that have huge branching factor, the player has lots of choices to decide. We cannot use the min-max algorithm, right? So where the choices are more, we cannot use this one. And where branching factor is more, we cannot use this one. And for chess game and Go game, all this, we cannot use this one. Okay. So this I'm stopping my class. Remaining topics becomes will be decided. I will discuss the remaining topics in the next class. Thank you.